everyone. Last time we looked at Exam 3, Topic 4, Part 1, so that was this page, where it was the integration of odd powers of tangent as long as there was a secant present. And recall the method was to isolate a secant tangent to make up the du, and then change everything else to secants. So we did that in those two examples from the previous video. So this is the second page of notes from Topic 4. And there's actually, this will be the last few examples, there's actually an overlap between the situations of Case 1 and Case 2 when tangent is odd and secant is even. So we're going to show both methods on the same problem and realize that one of them is going to be shorter than the other, and pretty much it's based on the fact that the powers of the tangents and secants respectively. So I'm going to rewrite the integral. We have the integral of tangent to the 11th of 3x, secant to the 4th of 3x, the differential dx. Okay, if we're going to use Case 1, which is the odd tangent, secant, any method, then we're one factor of each, tangent and secant, and push them over with the differential dx. So we're taking one factor of tangent away, tangent to the 10th of 3x, one factor of secant, secant cubed 3x, and we want to put them in the order. We don't want tangent secant, we'd prefer secant 3x, tangent 3x, because that's the way we memorize our formula for the derivative of secant. And at that point, we could ask the question, if our intent is for this secant tangent to be the du in the formula for the integral of u to the n, what would be the trigonometric function whose derivative is secant tangent? And that, of course, is secant. So if we could change the remaining factors of tangents to secants, we'll be able to start the u substitution process. And we can because we have the identity. Recall 1 plus tangent squared theta is secant squared theta. So if our interest is in tangent, we'll isolate tangent squared, be secant squared minus 1. We need tangent to the 10th, so as we've done in the past, you could think of that as tangent squared as a quantity to the 5th, which then is equivalent to secant squared minus 1 as a binomial to the 5th power. So that's our next move. So we get the integral of, again, secant squared 3x minus 1 accounts for 2 factors of tangent, but to account for 10 factors, we're going to have to raise that to the 5th power. We'll recopy the rest of this, the secant cubed 3x, and the secant 3x, tangent 3x dx, that we're saving for our du. And now's the point where we want to make a u substitution, because we forced our du to exist in the form of secant tangent, and we've changed everything else to be in terms of the u that produces that du, in particular that u being secant 3x. So from here, hopefully you're finding it somewhat routine, the du, secant 3x, tangent 3x, don't forget times 3, differential dx as well. Modifying 1/3 du is secant 3x, tangent 3x dx. Going back to the integral, u is secant, so here we have u squared minus 1, but as a quantity to the 5th. Here's u cubed, and then the secant 3x tangent 3x dx makes up 1/3 du. Okay, so our change of variables, bring out the 1/3 integral u squared minus 1, quantity to the 5th, u cubed, differential du. And we've seen this situation before, the fact that We know we can only integrate a sum or difference of terms of the form u to the n, and so we have to expand this binomial. It's to the 5th power. So remember, any binomial power 3 or greater, easiest way, Pascal's triangle and the binomial theorem. So I'll go off to the side, Pascal's triangle. You don't need to show this every single time. You can refer back to other instances that you may have done this. Okay, so spreading out the coefficients, 1, 5, 10, 10, 5, and 1. Okay, the signs are going to alternate because there's a difference between the two terms in the binomial. Always turning positive, negative, positive, negative, positive, negative. Okay, but be careful here. The thing is that in the past, this binomial was of the form either 1 minus u squared or 1 plus u squared. But now it's u squared minus 1. So when you deal with the powers, the pattern of the powers here, it's the first term u squared that gets raised to the nth or the 5th, and the second term 1 that gets raised to the 0. And so make special note of that. And then you decrease the first, so u squared to the 4th, increase the second, 1 to the 1st, and continue u squared cubed, 1 squared, u squared squared, 1 cubed, u squared to the 1st, 1 to the 4th, and finally u squared to the 0, and 1 to the 5th. So now that expansion yields u squared to the 5th, or u to the 10th, minus 5, u squared to the 4th, u to the 8th, plus 10, u squared cubed, u to the 6th, minus 5, u squared squared, u to the 4th. Oops, I'm sorry. 10, u to the 4th, plus 5, u squared to the 1st, u squared, and then minus, these are all 1s, so just 1. Okay, so the wavy line, back to the integration, 1/3 integral, that u squared minus 1 to the 5th is now replaced by what we just found, u to the 10th, minus 5 u to the 8th, plus 10 u to the 6th, minus 10 u to the 4th, plus 5u squared minus 1, and that's all times, don't forget the u cubed that's in there. And before we integrate, we have to distribute this u cubed. So 1/3 integral u to the 13th minus 5 u to the 11th plus 10 u to the 9th minus 10 u to the 7th plus 5 u to the 5th minus u cubed, all with respect to u. Now we have a sum or difference in terms of the form u to the n, and so now we can integrate term by term. So we'll recopy the 1/3, open up the brackets, integrate term by term, get u to the 14th over 14 minus 5, u to the 12th over 12, plus 10, u to the 10th over 10, minus 10, u to the 8th over 8, plus 5, u to the 6th over 6, and finally minus u to the 4th over 4. Close up the brackets, add the constant, and now distribute the 1/3. So we get 1 over 52 minus 5 over, oops, u to the 14th, excuse me. Minus 5 over 36, u to the 12th, Well, these 10s cancel, so we get plus 1/3. Here's a 10th. 10 over 8 is 5/4, so times 1/3 minus 5/12. E to the 8th. So 1/3 gives plus 5 over 18. E to the 6th. And then finally minus 1/12 u to the 4th plus c, and this is where u is equal to secant of 3x. So in terms of the overlap, so now we'll do the secant even method. It's basically the power that's going to dictate which one is more work. So tangent was, the 11th power was relatively high, especially in comparison to the 4th power. So that's what might trigger you to think that the even power secant method would be more advantageous in this case, as we're going to see. Because even power secant, remember, we're going to isolate 2 factors of secant to make up our derivative. So taking away 2 factors from secant to the 4th, we're left with secant squared. Secant squared 3x that we borrowed, push over with dx, box it off, save it. We want that to be our du. Logical question to ask, if secant squared is going to be the du, in the formula for the integral of u to the n, what's the function whose derivative is secant squared? And that, of course, is tangent. So if we could change the remaining factors of secant to tangents, we'll be able to start the u substitution process. The identity, recall, was 1 plus tangent squared theta is secant squared theta, so identically we can replace secant squared. So we're going to recopy this tangent to the 11th of 3x. The secant squared is 1 plus tangent squared of 3x. And then we have this secant squared 3x dx. That's saved to make up our du. And now we can start the u substitution process. We're going to pick our u to be the tangent of 3x. The du, secant squared 3x, don't forget times 3. Differential dx as well, routinely modifying. 1/3 du is secant squared 3x dx. Back to the integral. U is tangent, so here's u to the 11th. 1 plus u squared. And the secant squared 3x dx makes up 1/3 du. So change of variables, bring out the 1/3 integral to the 11th times 1 plus u squared with respect to u. And you can see this was a lot easier because now we don't need the binomial theorem or anything like that. All we have to do is distribute the u to the 11th. So we get 1/3 integral of u to the 11th plus u to the 13th with respect to u. And now we can integrate term by term. So the 1/3, open up some brackets, integrate u to the 11th, we get u to the 12th over 12. Integrate u to the 13th, u to the 14th over 14, close up the brackets, add our constant, and finally distribute that 1/3. So you get 1 over 36, u to the 12th, plus 1 over 52, u to the 14th, plus c. And this is where u is equal to tangent 3x. So the answers do look tremendously different. You can trust the same. This is, the 14th power here, but it's a secant, as opposed to here where it's a 14th power, but it's a tangent. If you actually substituted in the identities for tangent squared here, for these u's and literally expanded them and multiplied all the coefficients and everything, you could verify that it's the same as the other answer. But very tedious to do, so I would not recommend you even trying it, but at any point you want. Alright, so that's the end of topic 4, exam 3, and we'll come back and do topic 5 in a little bit.